Students, we are ready with our new topic, and this one is radioactivity. This one is radioactivity. Let us talk about the radioactivity, the phenomena of spontaneous radiation, the phenomena of spontaneous emission of radiation by a heavy element can be said as radioactivity. What I'm saying that the phenomena of spontaneous emission of radiation by a heavy element can be said as radioactivity. It was first discovered by Anthony Henry Becquerel in 1896. It was first discovered by Anthony Henry Becquerel in 1896. After that, it is confirmed by Pierre Curie and Marie Curie. And on the name of Becquerel, these penetrating rays are also called Becquerel rays. These rays are also called Becquerel rays. And then Rutherford concluded on the basis of this, when a radioactive element is bombarded, which is kept in lead cavity, then it is seen that some of the rays moves towards the positive plate nearby the lead cavity, and some of the rays moves towards the negative plate of the battery, and some goes undeviated. So the ray which moves towards the positive end of the battery, they are positively charged rays, and these rays are called alpha rays. And the rays which are attracted by the positive plate of the battery, that means they are negatively charged rays, and these rays are called beta rays. These rays are called what? Beta rays. And the rays which do not deviate in any direction, they are neutral rays, and they are known as gamma rays. So here we have got the three kinds of rays. The first one is alpha rays, the second one is beta rays, and the third one is gamma rays. Let us talk about the very first ray, that is alpha ray. Alpha ray are the positively charged rays. Alpha rays are the positively charged rays. They have rest mass equal to 4 times the mass of the proton. They are deflected by electric field and magnetic field. Likewise, beta are the negatively charged rays, and gamma are the neutral rays. So we are just having these the property. What are the properties of beta rays? They are deflected. They are also deflected by what? Electric field and magnetic field, and they affect photographic plates. But what about the gamma rays? They have no charge. Rest mass of gamma rays is 0. They goes undeviated. They are not deflected by electric field and magnetic field. What I'm saying? I'm saying these would be having the effect of electric field and magnetic field, but this would not have, because these are neutral and goes undeviated. I hope you have got these all phenomena, these all topics. Thank you, as this will see you in the next lecture. Thank you so much. Good morning, student. As this welcomes you all. Now we are ready with our new chapter. This one is nuclei. This one is second last chapter of your book, of your syllabus. We can say that. So let us start this chapter with the very first topic, that is nuclei. What do you mean by nuclei? Nuclei is the central core of an atom, which consists a positive charged particle and a neutral charged particle in it. What I'm saying it is the central core of atom, which consists positively charged particle and a neutral charged particle in it. That positive charged particle is called proton, and neutral particle is called neutron. It consists what? It consists proton and neutron in it. That is, and the electron revolves around it. These are the negatively charged particles which are revolving around it. So what is the composition of nuclei? What is the composition of nucleus? So composition of nucleus. Let us talk about the composition of nucleus. According to the Rutherford alpha scattering model, he suggested that the existence of some positively charged particle, charged particle within the region of an atom, and this positively charged particular region is treated as what? Nucleus. That means he suggested that there is a central core of an atom in which positively charged particles are present. That positively charged particles are known as proton, and the neutral particles which are kept with it, that is known as neutron. And it is said that almost all the mass of the atom is concentrated within the nucleus, containing positively charged particle like proton and the electrically neutral particle which is called what? Neutron in it. And a negatively charged particle electron revolves around it. So this was the composition of nucleus. So this is the composition of nucleus. In nuclei chapter, the very first heading what we have learned, this is nucleus. What is nucleus? The central core of atom, or the central region of an atom in which the positive charged particles and the neutral charged particles are concentrated or are kept. That is called what? Nucleus. Here the positively charged particles which are kept, that are known as proton, and the neutral particles are known as neutron. So what is the composition of nucleus? In the composition of nucleus, according to Rutherford alpha scattering model, Rutherford suggested that the existence of some positively charged region within the core of an atom, that is called proton, or this one is called nucleus. This one is called what? This one is called nucleus, and the electrons revolve around it. And the most important thing is that almost all the mass of an atom is concentrated over the nucleus. It is said by what? It is said by Rutherford. Now moving further, let us talk about other topic that is very acquainted with you all, that is atomic number. Atomic number is what? The number of atomic number. This is what? The number of proton or the number of electron present in an atom can be said as what? Atomic number. It is denoted by Z. The number of proton and the number of electron. The number of proton or the number of electron present in an atom can be treated as what? Atomic number of that particular atom, and it is denoted by Z. Now let us take another topic, that is atomic mass. What is atomic mass? Atomic mass is written like Z plus N. That means the number of proton and the number of neutron. The sum of number of proton and the number of neutron present in an atom can be said as what? Atomic mass of that atom. That means it can also be written like P plus N, or it can also be written like E plus N, because number of proton would always be equal to number of electron for an atom. So here, what is atomic number? The number of proton or the number of electron present in an atom can be said as what? Atomic number. And here, what is atomic mass? The sum of atomic number and the number of neutrons, we can say that. And in other words, we can say that the sum of number of protons and the number of neutrons can be said as atomic mass. So this is all about atomic number and atomic mass. I hope you got this particular introductory topics. Thank you, as this will see you in the next lecture. Good morning, students. Now we are ready with our new topics, that is, what do you mean by isotopes? What are the isotopes? Let me tell you, the atom of a particular chemical element having the same atomic number. What I'm saying? I'm saying that the atom of a particular chemical element having same atomic number same atomic number and different atomic mass, and different atomic mass is said to be isotopes, are said to be isotopes. I can write isotopes. So what are the example of isotopes? That this can be written like 6C10, 6C11, 6C12. These are the isotopes of carbon. That means there is one important thing what we have to concentrate over. There would be a particular chemical element. Now let us proceed for the isobars. What are the isobars? Isobars are the atoms of different, remember this point, of different chemical element, having same atomic mass but different atomic number, are treated as isobars. What can be the example of isobars? Isobars can be what? If I am writing 1H3 or 2He3, these are called isobars of one another. Likewise, if we are writing 3Li7 and 4Be7, then these are isobars of one another. Here we can see the atomic number is different but the atomic mass is same here also. So these are known as isobars. So we have read what? Isotopes and isobars. There is one more important topic, that is called isotones. What are the isotones? Let's see what are the isotones. I'm just writing it here. Isotones. The atoms of different chemical element having same number of neutron, can be said as isotones. Like what are the example of this? The example of this can be written like what? Beryllium and boron. Like 4Be9 and 5B10. It is having the same number of neutrons. So these are known as isotones of one another. So we have read here what? Isobars, isotones, isotopes. In the very first isotopes, the particular chemical element having same atomic number and different atomic mass. That means there would be the element would be same. That means if I am writing the isotopes of carbon can be, isotopes of hydrogen can be, but there should be a same chemical or a particular chemical element. Then isobars, we have read the isobars. Isobars are what? The different chemical element have what? Having the same atomic mass and different atomic number, that are known as isobars. Then here the same number of neutrons of different chemical element, that can be treated as what? Isotones. The same number of neutrons. I hope you have got this these all points, as this will see you in the next lecture. Thank you. Good morning students, as this welcomes you all. Now we are ready with our new topic, that is size of a nucleus. How will you find the size of a nucleus? As the resultant of Rutherford scattering model, Rutherford suggested what? Rutherford suggested that the size of a nucleus is linearly varying with the what? Mass number. The size of the nucleus varying with the mass number. That means size of nucleus is directly proportional to mass number. Is directly proportional to mass number. That means what? If we are taking nucleus as a spherical, as a sphere, so what would be there? Here, this would be what? Volume of nucleus. Volume of nucleus. If nucleus we are taking as radius of r, as radius of capital R, then how will you find this? That r is directly proportional to what? R is directly proportional to, no, not r, that is 4 by 3 pi r cube is directly proportional to a. This is constant value. This can be treated as constant, then r cube is directly proportional to a. This can be written like r is directly proportional to a by 3. This can be written like r is equal to r naught a to the power 1 by 3. Here, r naught is a constant which is known as empirical constant. Empirical constant. R is what? R is a empirical constant. So I was talking about size of the nucleus. In that we have read that, what we have read? We have read as the resultant of Rutherford scattering model, the size of nucleus was found to vary linearly with the mass number. The size of the nucleus was found to vary linearly with the mass number. As the nucleus is taken as a spherical, then the volume of a nucleus would directly proportional to the mass number, and here the volume of a sphere can be given like what? 4 by 3 pi r cube is directly proportional to what? A. Then we have taken 4 by 3 pi is a constant term, we have taken out, then r cube is directly proportional to a, that is r is directly proportional to a to the power 1 by 3, that is r is equal to r naught a to the power 1 by 3. Here r naught is an empirical constant, remember this always. And there would be the next topic, that is nuclear density. That is nuclear density. The next topic we are just going to study, that is nuclear density. So it can also be said as nuclear density. Rho is mass per unit volume. It is what? It is mass per unit volume of a nucleus can be said as mass per unit volume of a nucleus can be said as nuclear density of the particular nucleus. So what is that? It is the mass per unit volume. It is the mass per unit volume. If the value of volume is 1, then it is equal to the mass. Then we can say that mass per unit volume can be said as nuclear density. I hope you got this topic. As this, will see you again in the next lecture. Thank you. Morning students, as this welcomes you all. Now we are having a new topic. We are ready with a new topic, that is mass energy equation. What is mass energy equation? According to Einstein, it is like delta mc square. So here we will learn how to prove this. We know that there is a relation between mass and relativistic mass. There is a relation between mass and relativistic mass, and here how will you write that? M is equal to m naught upon under root 1 minus v square upon c square. This is the relation between the relativistic mass and the real mass. So this one is relativistic mass, and the relation can be given like this. So here we can write 1 minus v square upon c square power 1 by 2, that is m naught. Here we can write m c square minus v square, or just wait for a second or wait for a time, that is 1 minus v square upon c square can be written like 1 by 2 is equal to m naught. Here we know that 1 plus x to the power n is equal to 1 plus nx upon 1 factorial, likewise we can move. So that is what, in place of n, that can be multiplied inside, that is treated like 1 minus v square upon 2c square is equal to m naught. Up to this point it is clear, I hope. And here we can solve this. M 2c square minus v square upon 2c square is equal to m. From here we can just multiply m inside, that is m 2mc square minus mv square is equal to 2m naught c square. This can be taken this side, that is 2mc square minus 2m naught c square would be equal to mv square. This can be taken what? We can take 2 as common, 2c square as common, that is m minus m naught, and here mv square. Here this can be written like delta m, and this can be written like half mv square. This is the value of k max, or it is written like E, and this one is written like delta mc square. So this one is a proof of what? E is equal to delta mc square. This equation is called what? Mass energy equation. So this one is all about this particular topic. This is treated like what? Here m naught is what? Rest mass of this. Now moving further, there is another important topic, that is mass defect. That is mass defect, and this defect can be treated like what? If I am just writing here mass defect, it is clear by the name. It is clear by the name, that means there is a difference, or there is a difference in mass. So mass defect is what? It is the difference between the mass of constituent nucleons. It is the difference between the mass of a constituent nucleons of nucleus in the free state to the mass of a nucleus. That means what I am saying, if I am saying that the sum of proton and neutron, that can be said as nucleons. So it is the difference between the mass of the nucleons to the mass of the nucleus. That is written like what? I am just writing it here. It is written like mass of proton into Z plus mass of neutron A minus Z to the capital M. If capital M be the mass of a nucleus, then it can be written like what? Mass of proton into atomic number, that is number of neutrons into mass of neutrons minus the mass of the nucleus. So this equation represents what? Mass defect, and here delta M represents what? Mass defect. So mass defect is what? The difference between the mass of constituent nucleons, the difference between the mass of constituent nucleons to the mass of the nucleus. The difference between the mass of constituent nucleons to the mass of the nucleus is said to be what? Mass defect of that particular atom. I hope you have got these all points, as this will see you again in next lecture. Thank you. Now, we are ready with our new topic, and this topic is very important, that is nuclear binding energy. That is nuclear binding energy. Nuclear binding energy. The energy required, remember this thing, the energy required to disintegrate or to break. The energy required to disintegrate or to break the nucleus into its constituent particles, like nucleons, is said to be what? Nuclear binding energy. Nuclear binding energy is what? It is the energy required to disintegrate the nucleus into its constituent particles. And what are the constituent particles known as? That are known as nucleons. So it is the energy required to break or to disintegrate nucleus into its constituent particles. It is the value of this can be written like E is equal to delta mc square, and here E can be written like delta M can be written like what? Mass defect can be written like mp(z) plus mn E minus Z minus M into C square. If we are to just represent this in AMU, atomic mass unit, then it can also be written like E is equal to mp(z) plus mn E minus Z minus M AMU. If we are to write another form, then we can write delta M into 931 MeV, because 1 AMU is equal to 931 MeV. What I am saying? I am saying that 1 AMU is equal to 931 MeV. That is why it is written like this. Moving further, we are having another topic, that is nuclear binding energy. Nuclear binding energy per nucleon. Per nucleon. How will you just define this? This is the average energy required to release the nucleon from a nucleus what? This is the average energy required to, you can say that it is the average energy required to release a nucleon. It is the average energy required to release a nucleon from its nucleus, that is called nuclear binding energy per nucleon, and it is written like what? E average we can write here delta m into 931 upon me. So this is all about these two topics, that is nuclear binding energy per nucleon. So what is nuclear binding energy per nucleon? The average binding energy or the energy required, the average energy required to release a nucleon from a nucleus is called what? Nuclear binding energy per nucleon. I hope you have got these two topics. Thank you, as this will see you in the next lecture. Good morning, students. As this welcomes you all, now we are ready with our new topic, that is nuclear reaction. As we know that nuclear reaction is what? Nuclear reaction is the process by which a stable element is changed into another element. The process by which a stable element is changed into another element when it is bombarded by an energetic particle is called what? It's called nuclear reaction. As here I have shown a helium particle is bombarded over aluminum and it is making a silicon and a large amount of energy. Likewise, nuclear reactions are two types. Here, nuclear fission and the another one is nuclear fusion. What about nuclear fission? Let us talk about the nuclear fission. Fission means to break down. That means when a heavy radioactive element breaks into two lighter radioactive elements. When a heavy radioactive element breaks into two lighter radioactive elements and with the release of a large amount of energy, the process is said to be nuclear fission. Likewise, when two lighter radioactive elements combine together to form a heavier radioactive element, or when two light nuclei combine together to form a nucleus, can be said as nuclear fusion, and there is also a large amount of energy is being released. So let us see what is the example of this. When a uranium 232 is bombarded by neutron, 235 actually we are taking, is bombarded by neutron, it is converted into 92 uranium 236, which is unstable. Then it breaks into barium and krypton. It breaks into barium 56Ba 141 and krypton. What is the atomic number of krypton? That is 36 Kr 92 plus. Here what I said that large amount of energy is released. That is it. So here what we say, uranium breaks down into two smaller radioactive elements, that is barium and krypton. So the process is said to be nuclear fission. Now moving further, what is nuclear fusion? Nuclear fusion is the process when two light nuclei forms a heavier nucleus, that is called what? Nuclear fusion. That is, if we are taking the two elements of deuterium and they are combined to form one helium plus neutron and a large amount of energy is being released. So this process is said to be nuclear fusion. I hope you have got this topic, that when two lighter radioactive elements combine to form a heavier radioactive element, that is called what? Nuclear fusion. And when a heavier radioactive element breaks into two lighter radioactive elements, that is called nuclear fission. Thank you, as this will see you again next lecture. Good morning students. We are ready with our new topic. This one is law of radioactive decay, or this is also called law of disintegration. Law of disintegration. Here it is said that the rate of decay or the rate of disintegration of a radioactive element is always directly proportional to the number of nuclei present in that radioactive element. What I said that the rate of disintegration of a radioactive substance at any instant is directly proportional to the number of nucleus in the radioactive substance at that time. So this is written like minus dN by dt. Minus is just because it is decaying. It is decay. That means it is disintegrate itself. That is why it is written like this. Can be written like dn by dt is equal to lambda, and this can be written like what? dn by dt or dn by n is equal to lambda dt, and this negative sign can be taken at this place. Now we are just integrating it. Then what we get? We get that the integration is from what? N to n naught, or we can say that this can be converted like log n is equal to minus lambda t plus k. If t is equal to 0, then n becomes n naught. We are just putting this value here. Then log n naught is equal to k. We are putting in place of k. Then what we get? That log n is equal to minus lambda t plus log n naught. If you are taking this side, then this is written like log n minus log n naught is equal to minus lambda t. This is written like log m minus log n, that is log m by n. We should remember this, and this is written like this. And we know that when the log is removed, when the exponent form is being taken another side, so it is written like minus lambda, and here it is written like n is equal to n naught e to the power minus lambda t. This is radioactive law of disintegration, or the law of radioactive decay. The law of radioactive decay can be written like this. Moving further, there is another topic we have read. This I hope this derivation is clear to you all. I hope this derivation is clear to you all. Now moving further, there is another topic, that is half-life of radioactive element. That is half-life of radioactive element, and it is written like what? T half is equal to 0.6931 upon lambda. So we are just going to discuss the half-life of radioactive element. What do you mean by half-life of radioactive element? What we are going to discuss? Half-life of radioactive element. What is half-life of radioactive element? The time during which half of the nuclei of the radioactive substance disintegrates. As it is clear by the name, that is half-life. So we can say that the time during which the nuclei of the radioactive substance disintegrates, that is called half-life of that particular radioactive element, and its value can be given like T half is equal to 0.06931 by lambda, or another formula of this can be written like, if the relation between full life and half life is given, that is T is equal to n into T half. Clear? I hope you have got this particular topics. As this will see you again next lecture. Thank you so much.